this lesson we're going to be talking about linear equations again, but this time we're going to be looking a little bit more closely at tables. So if we're given a set of data in a table, the first thing we want to do is to assess whether the data is linear. So we're going to look to see that we have a constant rate of change. So if we look at the x and y data here, let's figure out how much each line is changing by. So we go from 2 to 6, that's an increase of 4. At the same time, x increased by 1. So I'm going to look at all my changes in y's, and these ones are all changing by 4. But let's make sure the x is also changing by the same amount relative to the y. Yep, every time we're going up by 1 here as well. So, 1. So, we've gone up by 4 every time on the y, 1 every time on the x. From before, we know that we're looking at rise over run. So that's y changes over x changes. So in our equation, we know that 4 is going to be our slope. Change in y over change in x, 4 over 1 is 4. But how do we determine the b value, the y-intercept? Well, we know from our graph that that's where it crosses the y-axis, and that's where the x value is 0. So if we look at a table and we see 0 for x, we can find the y value, and that's going to be our b value. So that's the equation for the first table. So let's go ahead and look at some more examples. Here we increased by 14. We did that again. 14 a third time, checking to make sure that we're getting that consistently. And so far, yep, every time we went up by 14. And we can see that the x's went up by 1 every time as well. So our equation will start off y equals 14x. Now again, for the b value, we look at, when x was 0, what was y? So instead of writing plus -3, we're just going to write minus 3. Great. Oh look, fractions, extra fun. So from 2 to 5 halves. Well, 2 is really 4 halves up to 5 halves, so that's an increase of 1 half. And then 5 halves plus another half would be 6 halves, or 3. So yes, it does go up by 1 half again, and 1 half again, and 1 half again, and finally 1 half a last time. And the x change is going up by 1 every time. So 1 half divided by 1 is simply 1 half. So our equation starts off y equals 1 half x. And again, we see when x is 0, y is 2. Perfect. All right, here we have decimals. This time we went from -4 to -3.75. So we increased by 0.25. And we can see that that is happening over and over again. We're going up by 0.25. Great. Up by 0.25. Up by 0.25. So our equation, and we're going to stick with decimals since the table was in decimals, 0.25x, and we started off at -4 there, so minus 4. Great. All right, here we go from 9 to 6. So we are this time decreasing by 3. So make sure you're paying attention to whether it's increasing or decreasing. When here we are decreasing by 3 every time, that's going to lead to the coefficient of x, our slope, being -3. Our x change is still positive, so we're still increasing by 1. And when we start the graph, when we have x at 0, we have y at 9. So we add 9. Okay, here we are in the negatives, but we are also decreasing as well. So down 4, down 4, down 4, and 2 more times. Great. So our slope, y equals -4x, but don't be quick to jump and just say it's this first number. Remember, as we've said every time, it's been when x is 0, what is y? But they didn't give us that here. So we have to do a little backtracking. If we subtracted 4 from something, we would get -7. Well, what would that something be? That would have to be -3. And the same thing would happen here if we went, down 1 from 1, we end up with 0. So we can work backwards in our table by following the same pattern, and we can get what we started with, what the y value would be when x is 0. So it is -3. So let's look at a few more examples here. So here we have an increase of 3, and that is happening repeatedly. And the x is increasing by 1 repeatedly. And again, we're not given when x is 0, but we could figure that out. Go back 3, and we would have had 5 there for y. So we're changing by 3 every time, so 3x, and we would have started with 5 when x is 0. So there's our equation. I'm going to skip around just a little bit. Let's jump over to number 9. Here we can see we decreased by 7, and again, we continue decreasing by 7 every time. 7. Here, though, we are left with our first value of x to be 2. If we need to go back 2 spots to 0, you could realize that we'd have to go back 14. So 14 taken away from something is 12. So that would have to be 26. So our equation for number 9, y equals negative 7x plus 26. Great. Now, number 10. Notice that we increased by 6, and again, and again, and again, and again. However, watch out, our coefficient of x, our slope, is not 6 because x is changing by 2. So up until now, every time we've seen a table, we've seen the x just increasing by 1. But here, every time, x is increasing by 2. So what we really need to consider is that it is the change in y, how much y is going up by, divided by how much x is going up by. So here, I'll write this in kind of like 2 steps here. So it's changing by 6 over 2. And it's starting at 0, negative 4, so minus 4. But let's clean that up a little bit. So we'll write that as y equals just 3x minus 4. So just because the y is changing by 6 doesn't mean that's going to be our coefficient of x. We need to think about what x is changing by as well. Great. So let's try to recap some of the things that we've talked about in the last 2 lessons. Let's first talk about constants. How do we see a constant in an equation and in a table? So let's start with in a table, since we just came from that. In a table, the constant is the y value when x is 0. So make sure we're not just defining it as the first y value. It is the y value when x is 0. In a graph, which we did previously, the constant is where the line crosses the y-axis, which we of course call the Y-intercept. Great. So let's just kind of add some visuals to our definitions there. So if we're given a graph, let's go ahead and say that we're looking at the equation y equals x plus 2. So x plus 2 would intersect there. I'm not going to make a super detailed graph because we're focusing just on the constant right now. But basically, that would be our graph. We see 2 on the y-axis. That is the same as the 2 that we have added on the constant at the end. In a table, if we have x and y, our table at some point is going to have x0, y2. For this equation, we would have also 1, 3, and 2, 4. Great. So that is a constant. That's how it looks in an equation, table, and graph. What about the coefficient? So in a table, we'll go back to that since we last were there. In a table, the coefficient is how much is the change in y divided by the change in x. In a graph, the coefficient is the rise over the run. So again, let's dive into a picture for that as well to support our words. So I'm going to make a little table here, a little graph first. So let's go ahead and let's make y equals 3x plus 1 into our example here. All right, so that is starting up 1, so that's where we're starting. If we go over 1, we'd have to go up 3 more. So these 2 points would be on the equation for this. So let me just extra point this out with some red here. So we're going up 3 over 1. That 3 over 1 is our coefficient. If we're in a table, okay, so we can start with 0 and 1 on their table. If we go up to 1, we're going to increase by 3 up to 4. Now, if the x value were to increase by 2, for instance, up to 3, we would know that the y value would have to increase by 6. So that's still, even though we see a different change in y here, change of 6, it still matches with x changing by 2 here. So that is still supporting our coefficient of 3. So we've talked a lot about slope and it being the coefficient of our equations for x. So now let's talk about putting equations in order from least steep to most steep when we're just given the equation. We don't have to take the time to graph them. So we're just looking at those coefficients. So our least steep is going to be the y equals 2x plus 2. We're just looking at that 2 in front of the x. After that will be y equals 3x plus 7. Yes, the 7 is big as the y-intercept, but that doesn't affect the slope. Next is y equals 6x plus 4. And finally, y equals 7x plus 2. Great. So, since we keep talking about slope, and you might have even heard me use a number of different terms interchangeably, let's make a list of all the different terms that we use to refer to the steepness of a linear function. One of them, of course, is slope. And we've talked about slope as a measure of rise over run. Rise over run could also sometimes be referred to as the change in y over the change in x. Very similarly, you might see that referred to as the Greek letter delta y over delta x. Delta is often the Greek symbol in science and math contexts for change. So you'll see delta y and delta x, meaning the same thing. Change in y, change in x. Another term that you might see is the constant of proportionality. This might really come into play when we're talking about maybe a geometry context or something where some scale factor has increased the size of something. There's a proportional relationship at play. We also, kind of a similar phrase, will talk about something called the constant of variation, which kind of sounds like an oxymoron. Constant staying the same, variation changing. How can this be an actual term? Well, if we think about linear functions are changing, but every time they're changing by the same amount. So constant variation means changing by the same amount every time. So a little bit counterintuitive, but it's something we'll talk about often. Another term we'll talk about is the rate of change. That kind of goes hand in hand. It doesn't imply that it has to be a linear rate of change, but in this unit we'll be focusing on the ones that are changing by a constant amount, a constant rate of change. When you get into upper levels, you'll start talking about derivatives, really in a calculus class. A derivative of a function is really looking at the rate of change of a function, and so a derivative is really a measure of the rate of change. Lastly, you might just see somebody talk about the rate in a variety of different contexts. All of those are different ways that we can talk about the steepness, the slope of a linear function. Well, what about the starting point of a linear function? Well, one thing, that's definitely our y-intercept. Certainly functions do start before x equals 0, start in the negatives, but a lot of times they do start when x is 0, and that's our y-intercept, so it's often our starting point. It might be our initial value, so some sort of scenario might take place, and wherever you start with might be the y-intercept, our starting point. It might be the beginning. So these are all kind of keywords that you might attach onto to think about when the graph starts. Another thing might be a flat fee. So if there's some sort of charge on something, the flat fee is your starting value. That might be a one-time amount, where it's not necessarily a fee, but it's something that happens once in the function, not over and over again. And lastly, a starting point, an original amount, any of these kind of ideas would be talking about a y-intercept. Let's now look at writing linear equations when we're giving a point and a slope. So we know that the form of a slope-intercept equation is y equals mx plus b. Well, ultimately, we've been given 3 out of the 4 pieces of information here. We've been given an x value, a y value, and m, the slope. So we're going to do what I often call a triple substitution. We're going to substitute the 3 values we know in, and we'll only have 1 value left. And so when there's only 1 unknown, we can solve that equation. So y is 2, m is 3/2, x is 4. We don't know b, but we can solve for it. So 2 equals 3/2 times 4. 2 goes into 2 once, 2 goes into 4 2 times, and 2 times 3 is 6. and we subtract 6 from both sides, and we get negative 4 equals b. Now, there's a tendency among students to say, oh, I got the variable, I solved it, I'm done, circle it, move on. No, remember, our goal is to write the slope-intercept form of the equation. So, slope-intercept form will always look like y equals mx plus b, and when it's finished, m and b should be replaced with numbers. They told us m, we found b, now we got to put it all together. We leave our y, we put back in our 3/2 slope, x stays in there because x and y are our variables. M and b, they're kind of variables, but they're kind of just placeholders until we find those values. B we just found as minus 4. So that's your answer. M and b have been replaced with the values that they are. X and y are still in there for our variables. Let's try at least one more. So again, y equals mx plus b. I would like you to be writing y equals mx plus b every time. Get in the habit of it. It'll help keep your work organized going forward. So let's make our triple substitution. So y is negative 2 equals negative 7/2. X is 2, add b. Great, we got to solve. Negative 2 equals, 2's cancel here, so just negative 7 plus b. We'll add 7 to both sides, and we'll get 5 equals b. So our equation is y equals, bring in our slope, negative 7/2. X, b we found is 5, so plus 5. Great. Let's look at just one other example of this type. So here we see this point that we're given is 0, 4. And if you're paying attention, you might recognize that this problem is basically done for us. We don't have to solve anything. When we have the x value as 0 and the y value is given to us, that's going to be our b value. So you might recognize right away that's b. So y equals 9/5 x is our slope, and b is 4. So nothing needed to do for that one. But we should check out a problem like number 9. The slope is undefined. From early on in this unit, we've talked about when the slope is undefined, we have a vertical line. Okay? A vertical line. A vertical line that's going to pass through this point is going to be an equation that's written x equals an integer. So if it's going to be x equals an integer and pass through this point, well, it's got to pass through negative 4. So x has got to be equal to negative 4. Not much work there. We just have to recognize that case. Now, if they had said the slope is 0, slope is 0 and going through this point, not the question we're asked for this time, but slope 0 going through that would be y equals 5, the y value. So be ready for either of those situations. Now, what happens if we're given 2 points? We're not given the slope. Well, we know that from 2 points we can find the slope. We have our slope formula, m equals y2 minus y1 over x2 minus x1. So we just have a step that we have to do before we can plug things into y equals mx plus b. So we'll plug into our slope formula. I'm going to take the second point, negative 5, minus negative 4 is plus 4, all divided by negative 3 minus 0. So in the numerator here we have negative 1, in the denominator we have negative 3, so our slope, negative 1 over negative 3, is 1/3. Now we are basically where we were from the previous set of problems. So we're going to go to y equals m, x plus b. But wait, we have 2 points. What are we going to plug in? Well, you actually get the choice. You can plug in either point. If you're really extra cautious, you could do it once with the first point and do it once with the second point and make sure you got the same answer. That'd be a nice way to double check your work. I'm going to go ahead and pick 0, negative 4 to plug in. You could pick whatever one you think might be easiest to plug in, and that's fine with me. So we're going to plug negative 4 in for y equals 1/3 times 0 plus b. We don't know b yet. Great. Okay, so that's negative 4. 0 times anything is 0. Great, and you might have even recognized right away, as we did in the previous problem, if they give us 0, and the number, that is b. So we could have even jumped there right away, and this is kind of why, because 0 times the x value just disappears, and so you can see right here that we have our b value. So our equation equals y equals 1/3 is our slope, x minus 4. Great. So if they give us the 0, comma, a number, that's already our y-intercept, great. What happens if they don't? Let's go ahead and just try another one like number 17. So number 17, we have to start off by finding the slope. So m equals y2 minus y1 over x2 minus x1. Make sure you're getting those y's on the top every time. So m equals, we're going to do 5 minus negative 4, so 5 plus 4, over 5 minus 4. So that's 9 over 1. So our slope is 9. So y equals mx plus b. Totally your preference on which points you plug in. I might choose 5, 5. No negatives on that one. So 5 equals 9 for our slope, 5 for x, plus b. So 5 equals 45 plus b. So we subtract 45 from both sides, and we get negative 40 equals b. So don't stop there. Finish it off. Your equation is y equals 9x minus 40. Great. In our last set of problems, we have equations that are already written. They're just not written in slope-intercept form. Slope-intercept form, of course, is y equals mx plus b. You've heard that probably 1,000 times already today. So we notice that in our slope-intercept form equations, y is all by itself. That's what we're going to strive for here today. So this really summons back those skills we used when we were doing literal equations. This is a literal equation that we have to solve for y. So we're going to start by subtracting 13x, getting away anything we want to that was added or subtracted to the y term. So we're going to do that on both sides. Now, when I do this, I'm going to start putting things in the right order. So because mx comes first, I'm going to write negative 13x, and this is a positive 28 second. Great. Then I'm going to go ahead and divide both sides by negative 4. Now, over here, I could divide the whole thing by negative 4, but I'm going to divide each term by negative 4. That would be kind of our next step anyways. So y equals negative 13 over negative 4. We'll just clear up the signs there and just make that 13/4. Do not put mixed numbers in an equation, because then it'll be confusing. Like, is this 3 and 3 times 1/4 times x? You know, what is that number? So we don't want to have a mixed number in there. Leave it as an improper fraction. And then 28 divided by negative 4 is negative 7. So there's our equation. We just had to solve it like a literal equation for y. We might see some slightly different examples, but shouldn't be anything too scary. So for this one, we have to distribute the 5/4 first. So 5/4 times x is 5/4 x, and 5/4 times 1 is 5/4. So I need to solve for y, so I need to get rid of this minus 2. So I'm going to add 2 on this side. When I do it on this side, I'm going to add a version of 2. I'm going to add 8/4. 8/4 is 2, but see how I've set it up to already be a common denominator with the 5/4, and I even wrote it right underneath the 5/4 to make it easy. So we have y over here, 5/4 x, and 5 plus 8 is 13/4. And so that is our equation.